Hello and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're going to explore one of the most captivating questions in modern astronomy: where exactly can life exist beyond Earth? We'll journey through the habitable zones around different types of stars, those special regions where conditions might be just right for liquid water to pool on planetary surfaces. We'll discover why the same distance that works for one star might be frozen wasteland or scorched desert around another. We'll examine how astronomers calculate these regions, what makes them shift and change, and why finding them has become central to our search for worlds that could harbor life. If you enjoy these types of videos about the cosmos and the mysteries it holds, please consider giving this video a thumbs up and subscribing to the channel. I'd also love to know where you're watching from and what time it is in your corner of the world. Drop a comment below and let me know. Let's dive in. The concept of a habitable zone, sometimes called the Goldilocks zone, is beautifully simple at its core. Just as the porridge in the fairy tale needed to be neither too hot nor too cold, a planet needs to orbit at just the right distance from its star to maintain liquid water on its surface. Too close, and water boils away into steam. Too far, and it freezes into ice. This narrow band around a star represents the sweet spot where temperatures allow water to remain in its liquid state, at least theoretically. The idea itself dates back to the 1950s and 60s, when astronomers first began seriously considering where life might exist beyond our solar system. Scientists like Su Huang proposed that each star would have its own region where conditions could be suitable for life. The boundaries of this zone depend entirely on how much energy a star radiates. A hotter, brighter star pushes the habitable zone farther out. A cooler, dimmer star brings it much closer in. Think of it like a campfire on a cold night. If you're sitting too close, you'll be uncomfortably hot. Too far away, and you won't feel the warmth at all. There's a perfect distance where you're just comfortable enough. That distance changes depending on how large and hot the fire is burning. A roaring bonfire requires you to sit much farther back than a small campfire to feel that same comfortable warmth. Our own Earth sits comfortably within the Sun's habitable zone, orbiting at about 93 million miles away. This distance gives us an average temperature that keeps our oceans liquid and our atmosphere stable enough to support the incredible diversity of life we see today. Venus, our inner neighbor, orbits too close. Its surface temperature exceeds 800 degrees Fahrenheit, hot enough to melt lead. Mars, our outer neighbor, sits near the edge of the habitable zone where conditions are much colder, though scientists believe it may have had liquid water on its surface billions of years ago when it was warmer. The boundaries of a habitable zone aren't sharp lines, but rather fuzzy regions where conditions gradually transition. Astronomers define the inner edge as the point where a planet would experience a runaway greenhouse effect, causing all water to evaporate into the atmosphere. The outer edge is where carbon dioxide, even at maximum atmospheric pressure, would freeze out of the atmosphere entirely, making it impossible for the greenhouse effect to warm the planet enough to maintain liquid water. These calculations require astronomers to consider many factors. The star's luminosity, or total energy output, is the primary factor. But planetary characteristics matter too. A planet with a thick atmosphere can trap more heat, potentially making it habitable even farther from its star. A planet with no atmosphere at all might be frozen even within what we'd normally consider the habitable zone. The presence of greenhouse gases, reflective clouds, and even the planet's rotation rate all play roles in determining whether liquid water can actually exist. Stars come in an astonishing variety of sizes, temperatures, and brightnesses. Astronomers classify them using a system based on their surface temperature, ranging from the hottest O-type stars, which burn blue and white, through cooler B, A, F, and G types, down to the coolest M-type stars, which glow a dim red. Each type of star creates a different habitable zone, and understanding this diversity is crucial to our search for potentially inhabited worlds beyond our solar system. Our Sun is a G-type star, sometimes called a yellow dwarf, though its light actually appears white when viewed from space. With a surface temperature around 10,000 degrees Fahrenheit, the Sun represents a middle ground in the stellar spectrum. It's neither the hottest nor the coolest, neither the brightest nor the dimmest. This middle position has important implications for Earth's habitability, giving us a stable, long-burning star that will shine steadily for billions of years. At the hotter end of the spectrum, we find the massive, luminous stars that burn through their fuel at incredible rates. An O-type star might shine with the brightness of a million suns, flooding space with intense radiation. The habitable zone around such a star would extend incredibly far out, potentially dozens of times Earth's distance from the Sun. However, these brilliant stars are rare and short-lived, burning through their fuel in just a few million years. Life as we know it requires billions of years to evolve, making these stellar giants poor candidates for hosting inhabited worlds, despite their expansive habitable zones. Moving down the scale, we encounter stars more similar to our Sun. F-type stars burn slightly hotter and brighter, pushing their habitable zones somewhat farther out. K-type stars, orange dwarfs, burn cooler and dimmer, pulling their habitable zones closer in. These stars are particularly interesting to astronomers because they're numerous and long-lived. A K-type star might burn steadily for 15 to 30 billion years, far longer than our Sun's 10 billion year lifespan, potentially giving life even more time to arise and flourish. The most common stars in our galaxy are the M-type red dwarfs, small, cool stars that burn their fuel so slowly they could theoretically shine for trillions of years. These dim stars make up roughly 75% of all stars in the Milky Way. Their habitable zones hug very close to the star itself, sometimes closer than Mercury orbits our Sun. This proximity creates unique challenges and opportunities that we'll explore further, but the sheer abundance of these stars makes them prime targets in the search for habitable worlds. If even a small fraction of red dwarfs host habitable planets, the galaxy could be teeming with potential homes for life. Temperature isn't the only factor that matters. Stars also vary in their stability. Young stars, regardless of type, tend to be more active, producing powerful flares and varying in brightness. As stars age and settle into their main sequence, the long stable period where they burn hydrogen into helium, they become more reliable sources of energy. Our Sun is currently in this comfortable middle age, having burned steadily for about 4.5 billion years with roughly 5 billion more to go. The color of a star's light also affects how photosynthesis might work on planets around it. Plants on Earth evolved to harness the Sun's yellow and white light, appearing green because they reflect green wavelengths while absorbing red and blue. On a planet around a red dwarf, plants might appear black to capture as much of the dim red light as possible. Around a hotter blue star, photosynthetic organisms might take on entirely different colors to optimize for the bluer wavelengths available. Determining where the habitable zone lies around any given star requires sophisticated calculations that account for the intricate dance between stellar radiation and planetary atmospheres. Astronomers have developed mathematical models that take a star's properties and translate them into concrete distances where liquid water could theoretically exist. These calculations have evolved considerably since they were first proposed, becoming more nuanced as our understanding of planetary atmospheres has deepened. The most fundamental input to these calculations is stellar luminosity, the total amount of energy a star radiates per second. Luminosity depends on both the star's size and its surface temperature. A star twice as wide as our Sun, but with the same surface temperature, would have 4 times the surface area and therefore emit 4 times as much light. Temperature has an even more dramatic effect. A star with twice the surface temperature radiates 16 times as much energy per unit of surface area. This fourth power relationship makes temperature the dominant factor in determining a star's brightness. Once astronomers know a star's luminosity, they can calculate the habitable zone using the inverse square law of light. This law states that the intensity of light decreases with the square of the distance from the source. Double your distance from a light source, and you receive 1/4 the light. Triple the distance, and you get 1/9. This mathematical relationship allows scientists to find the distances where a planet would receive just the right amount of starlight to maintain liquid water. For the inner edge of the habitable zone, calculations focus on the runaway greenhouse threshold. At this critical point, incoming stellar radiation becomes so intense that water begins to accumulate in the atmosphere as vapor. Water vapor is itself a greenhouse gas, trapping even more heat. This creates a feedback loop where more heat leads to more water vapor, which traps more heat, which evaporates more water. Eventually, all surface water boils away, and the planet ends up like Venus, with a thick, hot atmosphere and a surface too scorched for any liquid water to remain. The outer edge calculations involve the opposite problem: maximum greenhouse warming. Even with a thick atmosphere full of carbon dioxide and other greenhouse gases, there's a distance beyond which a planet simply can't trap enough heat to prevent water from freezing. At these distances, even the most optimistic atmospheric conditions can't maintain temperatures above the freezing point of water. The planet becomes a frozen world, with any water locked away in ice sheets and glaciers. Modern calculations recognize that these boundaries aren't fixed lines but probability gradients. Some models define a conservative habitable zone, where we're quite confident liquid water could exist, and an optimistic habitable zone, where special conditions might allow it. The conservative zone is narrower and represents the safest bet for finding habitable conditions. The optimistic zone extends farther in both directions, encompassing planets where habitability is possible but requires more favorable circumstances. Astronomers also consider something called the continuously habitable zone, which accounts for how stars change over time. A star like our Sun gradually brightens as it ages, increasing its luminosity by about 10% every billion years. This means the habitable zone slowly moves outward over time. A planet might start out comfortably within the habitable zone when the star is young, but eventually find itself too close as the star brightens. The continuously habitable zone represents the narrow band where a planet would remain habitable throughout the star's entire main sequence lifetime, potentially billions of years. Red dwarf stars present one of the most intriguing and controversial cases in the search for habitable worlds. These small, cool stars are the runts of the stellar litter, with masses as low as 8% that of our Sun. Their low mass means they burn their hydrogen fuel incredibly slowly, allowing them to shine for potentially hundreds of billions or even trillions of years. Given that our universe is only about 14 billion years old, not a single red dwarf has yet reached the end of its natural lifespan. This longevity makes them attractive targets for finding habitable worlds, but their unique properties also create significant challenges. The habitable zone around a red dwarf sits remarkably close to the star. For a star like Proxima Centauri, the nearest star to our Sun, the habitable zone lies only about 5 million miles from the star, roughly 7% of Earth's distance from the Sun. A planet in this zone would orbit its star much faster than Earth orbits the Sun, potentially completing a full year in just 10 to 20 Earth days. From the planet's surface, the red dwarf would appear much larger in the sky than our Sun does from Earth, glowing a deep red or orange color. This proximity creates a phenomenon called tidal locking, similar to how our moon always shows the same face to Earth. When a planet orbits very close to its star, gravitational forces cause the planet's rotation to slow until it spins once per orbit, keeping one hemisphere perpetually facing the star and the other in eternal darkness. Imagine a world where one side experiences endless day, growing hotter and hotter, while the other side faces endless night, growing colder and colder. The only comfortable region might be the twilight zone between these extremes, a thin band where the sun hangs perpetually at the horizon. However, recent studies suggest that tidal locking might not be as catastrophic as once thought. If the planet has a thick enough atmosphere, winds could transport heat from the day side to the night side, moderating temperatures across the planet. Computer simulations show that atmospheric circulation patterns could create habitable conditions even on tidally locked worlds. Some models even suggest that the permanent twilight zone could provide stable, temperate conditions more favorable than the constantly changing environment we experience on Earth. Red dwarfs are also prone to dramatic stellar flares, sudden explosions of energy that can temporarily increase the star's brightness by orders of magnitude. These flares release intense ultraviolet and X-ray radiation that could strip away a planet's atmosphere or sterilize its surface. Young red dwarfs are particularly active, producing powerful flares regularly. However, as these stars age and their rotation slows, they generally become more placid. A planet around an old, quiet red dwarf might experience a relatively stable environment despite the star's diminutive size. Another concern involves the type of light red dwarfs emit. These stars produce most of their energy in the infrared part of the spectrum, with relatively little visible light. Photosynthesis as we know it might be challenging under such dim, red illumination. However, life is remarkably adaptable. Some scientists propose that organisms on red dwarf planets might evolve to use the infrared light, or they might gather in large colonies to pool the limited light available, similar to how certain bacteria on Earth function in low-light environments. Despite these challenges, the discovery of planets around red dwarfs has accelerated in recent years. The TRAPPIST-1 system, located about 40 light-years from Earth, contains 7 Earth-sized planets orbiting a cool red dwarf. At least 3 of these planets sit within the star's habitable zone, making this system one of the most promising places to search for life beyond our solar system. Proxima Centauri, our nearest stellar neighbor, hosts at least one planet, Proxima b, that orbits within the habitable zone. These discoveries have transformed red dwarfs from astronomical curiosities into primary targets in the search for inhabited worlds. Stars similar to our Sun represent perhaps the most straightforward case for habitability, simply because we have a working example right in our cosmic backyard. These G-type yellow dwarfs, along with their slightly cooler K-type orange dwarf cousins, create habitable zones that are wide, stable, and located at comfortable distances where tidal locking is unlikely to occur. Understanding these stars helps us appreciate why Earth has remained habitable for billions of years and where we might find similar success stories around other stars. The Sun's habitable zone extends from roughly 93 million miles at its inner edge to about 140 million miles at its outer edge, depending on which calculation method you prefer. Earth orbits at 93 million miles, placing us right near the inner edge of this zone. Venus, at 67 million miles, is too close, while Mars, at 142 million miles, sits right at the outer boundary. This positioning explains much about the three planets' vastly different climates. What makes Sun-like stars particularly promising for life is their stability and longevity. These stars burn through their hydrogen fuel at a moderate rate, maintaining steady output for about 10 billion years. This time span is crucial because life on Earth required roughly 4 billion years to evolve from simple microbes to the diverse biosphere we see today. Stars that burn much faster than the Sun might not provide enough time for similar evolutionary processes to unfold. The spectrum of light from Sun-like stars is also well suited for chemistry and biology. These stars emit significant energy across visible wavelengths, from red through violet, along with ultraviolet and infrared radiation. This broad spectrum provides energy for various chemical reactions and photosynthetic processes. The moderate ultraviolet output is enough to drive important atmospheric chemistry, creating an ozone layer that protects surface life from excessive radiation, but not so much that it would sterilize planetary surfaces. K-type orange dwarfs might actually be even better candidates for hosting life than Sun-like stars. These stars are cooler and dimmer, but they're also more numerous and longer lasting. A typical K-dwarf might shine steadily for 20 to 30 billion years, giving life more than twice as long to arise and evolve compared to planets around Sun-like stars. Their habitable zones are closer in than the Sun's, but not so close that tidal locking becomes inevitable. Planets in these zones would still have distinct days and nights, seasons, and weather patterns similar to what we experience on Earth. Scientists have identified numerous Sun-like stars with planets in their habitable zones. Kepler 452b, for instance, orbits a G-type star about 1,400 light-years away. This planet is about 60% larger than Earth and orbits within its star's habitable zone at a distance similar to Earth's orbit around the Sun. It receives about 10% more stellar energy than Earth does, potentially making it slightly warmer, but still within the range where liquid water could exist on its surface. Another promising system is Kepler 186f, which orbits a cooler star and takes 130 days to complete its orbit. This planet sits near the outer edge of its star's habitable zone and receives about 1/3 the light Earth gets from the Sun. If it has a thick atmosphere with sufficient greenhouse gases, it could maintain liquid water despite the reduced sunlight. These examples demonstrate that habitable zone planets around Sun-like stars aren't merely theoretical but actual worlds we can observe and study. The challenge now is determining whether any of these planets actually harbor life. Current telescopes can detect the planets and measure their sizes and orbits, but determining atmospheric composition and surface conditions requires more sophisticated instruments. Future telescopes will analyze the light passing through these planets' atmospheres as they cross in front of their stars, searching for chemical signatures like oxygen, methane, or other gases that might indicate biological activity. At the opposite end of the stellar spectrum from red dwarfs, we find the massive, brilliant stars that illuminate space with dazzling intensity. These hot stars, particularly A and F types, create habitable zones that extend far from the star, sometimes several times the distance between Earth and the Sun. However, despite their expansive habitable regions, these stellar giants present significant obstacles for the development of life. An A-type star might have twice the mass of our Sun and burn with 4 to 5 times the luminosity. This brightness pushes the habitable zone outward to perhaps twice Earth's distance from the Sun or even farther. F-type stars, slightly cooler than the types but still hotter than our Sun, create similarly expanded habitable zones. A planet in one of these distant habitable zones would receive the same amount of warmth as Earth does despite orbiting much farther from its star, thanks to the star's greater luminosity. The most significant problem with hot stars is their brief lifespans. An A-type star might shine for only 1 to 2 billion years before exhausting its hydrogen fuel and swelling into a red giant. F-type stars last longer, perhaps 3 to 4 billion years, but this is still short compared to the time life required to evolve on Earth. The first billion years of Earth's history saw only simple single-celled organisms. Multicellular life didn't appear until around 600 million years ago, and intelligent life capable of technology arose even more recently. Hot stars might simply not provide enough time for similar evolutionary processes. Another challenge involves stellar activity and radiation. Hot stars emit substantial amounts of ultraviolet radiation, far more than cooler stars produce. While some ultraviolet light is necessary for certain atmospheric chemistry, too much can be harmful. Excessive ultraviolet radiation can break apart water molecules in a planet's upper atmosphere, allowing hydrogen to escape to space. Over time, this process could strip away a planet's water, leaving it dry and barren even if it starts with abundant oceans. The rapid evolution of hot stars also means their habitable zones move dramatically over time. As these stars age and brighten, the habitable zone shifts outward more quickly than around cooler stars. A planet that begins its existence in the habitable zone might find itself too close to the star within a few 100 million years as the star's output increases. This rapid environmental change would challenge any nascent life trying to establish itself. Despite these difficulties, planets around hot stars aren't completely impossible candidates for life. Some scientists propose that life could arise more quickly than it did on Earth under the right conditions. Additionally, advanced civilizations might colonize these systems, appreciating the brilliant light and abundant energy these stars provide. The expanded habitable zones could even accommodate multiple habitable planets, creating solar systems with several Earth-like worlds orbiting at different distances. Detecting planets around hot stars presents technical challenges. These stars spin rapidly and have fewer surface features than cooler stars, making precise measurements difficult. The brilliant light can also overwhelm the faint signal of planets, making them harder to spot. Nevertheless, astronomers have discovered planets around these stars, and some orbit within the habitable zone. Whether any of these worlds could support life remains an open question. One will need better telescopes and more detailed observations to answer definitively. While stellar properties define the basic boundaries of a habitable zone, planetary characteristics determine whether a world within that zone actually maintains habitable conditions. Two planets orbiting at the same distance from identical stars could have completely different climates depending on their size, composition, atmosphere, and geological activity. Understanding these factors helps astronomers refine their search for truly habitable worlds beyond our solar system. Atmospheric composition plays perhaps the most critical role. Earth's atmosphere, composed primarily of nitrogen and oxygen with trace amounts of carbon dioxide and other gases, creates a moderate greenhouse effect that warms our planet by about 60 degrees Fahrenheit above what it would be without an atmosphere. This warming is essential for keeping water liquid across much of the planet's surface. Too little atmosphere, like Mars, and a planet freezes. Too much, like Venus, and it roasts under an extreme greenhouse effect. The presence of water itself profoundly affects habitability. Water has an extraordinarily high heat capacity, meaning it can absorb and store large amounts of heat without changing temperature dramatically. Oceans act as thermal buffers, moderating a planet's climate and preventing extreme temperature swings. Water also plays a crucial role in weathering rocks and regulating carbon dioxide levels in the atmosphere through a feedback mechanism that helps stabilize climate over long timescales. Planetary size matters because it determines surface gravity, which affects a planet's ability to retain an atmosphere. Smaller planets, with weaker gravity, more easily lose their atmospheric gases to space. Mars, with only 1/3 Earth's gravity, has gradually lost most of its atmosphere over billions of years. Larger planets can hold onto their atmospheres more tenaciously, but if they grow too large, they become gas giants that lack a solid surface altogether. The sweet spot appears to be somewhere between half and twice Earth's size. Geological activity, particularly plate tectonics, also contributes to habitability. On Earth, the slow movement of crustal plates recycles carbon between the surface and interior, regulating atmospheric carbon dioxide levels over millions of years. This geological carbon cycle helps maintain stable temperatures despite the sun's gradually increasing brightness. Volcanic activity releases gases that replenish the atmosphere, while subduction zones pull carbon-bearing rocks back into the interior. Planets without active geology might lack these stabilizing mechanisms. A planet's magnetic field provides protection from stellar radiation and solar wind, streams of charged particles that flow outward from stars. Earth's magnetic field, generated by the motion of molten iron in our planet's core, deflects much of this radiation, preventing it from stripping away our atmosphere. Mars lacks a strong magnetic field and has consequently lost much of its atmosphere to space. For planets around active stars that produce intense radiation, a protective magnetic field might be essential for maintaining habitability. Orbital characteristics also influence climate stability. Earth's nearly circular orbit keeps us at a fairly constant distance from the Sun throughout the year. A highly elliptical orbit would cause dramatic swings in the amount of energy a planet receives, potentially making climate unstable. The tilt of a planet's rotational axis creates seasons, which drive atmospheric circulation and help distribute heat around the planet. Too much tilt could lead to extreme seasonal variations, while no tilt would eliminate seasons entirely. Even factors like the presence of a large moon can affect habitability. Our moon stabilizes Earth's axial tilt, preventing dramatic wobbling that would cause severe climate swings. The moon also drives tides that may have played a role in the transition of life from ocean to land. These subtle factors remind us that habitability emerges from a combination of many conditions working together, not just a planet's distance from its star. The search for habitable worlds has evolved dramatically over the past few decades, transforming from theoretical speculation to observational science. As our telescopes become more powerful and our techniques more refined, we're discovering that planets are incredibly common and that many orbit within their stars' habitable zones. The next challenge is determining which of these worlds actually possess conditions suitable for life and whether any of them host biological activity. Current technology allows us to detect planets primarily through two methods. The transit method watches for the slight dimming of starlight when a planet passes in front of its star. The radial velocity method measures the subtle wobble in a star's motion caused by the gravitational pull of orbiting planets. Both techniques have been tremendously successful, revealing thousands of planets around other stars. However, these methods tell us about a planet's size and orbit but reveal little about its atmosphere or surface conditions. The next generation of space telescopes will change this dramatically. These instruments will analyze starlight filtering through planetary atmospheres as planets transit their stars. By examining which wavelengths are absorbed, astronomers can identify atmospheric gases. The presence of oxygen, methane, and water vapor together might indicate biological activity, since these gases react with each other and would normally disappear unless continuously replenished by living processes. Finding such biosignatures would revolutionize our understanding of life's prevalence in the universe. Ground-based telescopes are also becoming more capable. Enormous instruments will have mirrors over 30 meters across, gathering more light than any previous optical telescope. These giants will be able to directly image some planets around nearby stars, capturing actual photographs of these distant worlds. While they'll appear as mere pinpoints of light, even that will allow astronomers to study how the planet's brightness changes, potentially revealing the presence of clouds, oceans, or continents. Our understanding of habitable zones continues to evolve as scientists discover new factors that influence habitability. Recent research suggests that planets with extensive cloud cover might remain habitable much closer to their stars than previously thought, as the clouds reflect incoming starlight. Other studies show that planets with subsurface oceans, like Jupiter's moon Europa or Saturn's moon Enceladus, might harbor life even far outside the traditional habitable zone. These discoveries are expanding our conception of where life might exist. Scientists are also beginning to consider the concept of a galactic habitable zone, a region within the Milky Way galaxy where conditions are most favorable for life. Too close to the galactic center, and frequent supernovae and intense radiation might sterilize planets. Too far out in the galactic outskirts, and there might not be enough heavy elements to form rocky planets. Our solar system sits in what might be a favorable region, about 2/3 of the way from the galactic center, where conditions are just right for life to flourish. The discovery of thousands of planets has also revealed that planetary systems are more diverse than we ever imagined. We've found hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths larger than our planet but smaller than Neptune, and systems where multiple planets orbit in tight formation. This diversity suggests that planet formation and evolution are more variable than our single example, the solar system, led us to believe. Each discovery refines our understanding of how planetary systems develop and where habitable worlds might arise. Looking ahead, the search for habitable worlds and potential life beyond Earth will intensify. Within the next few decades, we may detect chemical signs of life in the atmosphere of a planet orbiting another star. We might identify dozens or even hundreds of potentially habitable worlds within a few hundred light years of Earth. Each discovery will help us understand whether life is common or rare, whether Earth is typical or unusual, and whether intelligence like ours emerges readily or represents an extraordinary cosmic fluke. And on that note, we reach the end of our journey through the habitable zones of distant stars. We've explored how these regions of potential habitability change with stellar type, how planetary characteristics determine whether worlds within these zones can actually support liquid water, and how our understanding continues to evolve with each new discovery. The search for habitable worlds represents one of humanity's most profound scientific endeavors, touching on questions about our place in the universe and whether we're alone among the stars. Thank you for joining me tonight on the Nocturnal Astronomer. I hope these ideas have given you something to contemplate as you drift off to sleep or simply provided a peaceful companion to your evening. Until next time, keep looking up at those stars and wondering what worlds might circle them, and what stories those distant planets might tell if we could only visit them.